So you have this table on your sheet. If you so anytime I need to get extra stuff, or I look at it and I'm like, I don't think this has everything it needs, definitely check out that sheet and check out that part of the table, or that top part of your sheet, and it may have that extra information that you need. So let's go ahead and get started. And I try to work these out ahead of time, but like I said, I've been sick and math is not my strong suit. So if something is a little off, the math is off, just please send me an email and I'll look over it and see, because like I said, I'm going to try my best to not screw up any math, but math is not my strong suit, especially when I'm sick. So, okay, so this one asks how many kilowatt of energy could be generated by a coal-burning power plant that burned 250 tons of coal and was 40% efficient. So there's two ways you can approach this problem. You can do the 250 tons and you can take 40% of that, or you can just take the 40% off at the end. I prefer to take the 40% off at the end. Okay, let's try this again. I'm trying to put my hand on the screen and it's not liking it. Okay. 150 tons. Okay. So what I'm going to do is I'm going to convert these tons to BTUs, and that's a conversion I got from that table on the first page, on the first slide. And 2.5 times 10 to the 7. Okay. And then I'm going to convert these BTUs to kilowatt hours, because that's what it's asking for. And again, this conversion is on the table on the front slide and at the top of your paper. Okay, so this gives me 1.83 times 10 to the 6 kilowatt hours. And now I'm going to take my 40%. Okay, so I'm going to multiply that by 0.4. And that's going to give me 7.32 times 10 to the 5 kilowatt hours. I'm not going to count sig figs and all that stuff. If you want to write the whole thing out instead of scientific notation, that's fine. But
okay, now let's try problem 2. So in this problem, they're asking us how much natural gas must be burned in order to produce, let me get a thicker pen. There we go. 5.2 times 10 to the 4 kilowatt hours of electricity if the power plant was 65% efficient. And so here's what we're going to do. We're going to take this 5.2 times 10 to the 4 kilowatt hours. And don't forget that times 10 to the 4. I see a lot of students do that. And then what we're going to do is we're going to convert this to BTUs first. So we're going to get 3413 BTUs. And I'm just getting this from, this information they gave us at the beginning, where we have a kilowatt hour is 3413 BTUs, and then we'll also be using this one. 1 cubic foot of gas contains 1031 BTUs of energy eventually. Okay, so we have 34.13 BTUs over 1 kilowatt hour. And I chose that one because I wanted to get rid of kilowatt hours. Okay, So I'm going to go from kilowatt hours to BTUs. And then I'm going to go to BTUs to cubic feet. So since I want to get rid of BTU and I've got BTU up here, I'm going to put the 1031 on the bottom and I'm going to put the 1 cubic foot on the top. Okay, and that'll get rid of my BTUs. So then I'm going to take, I'm going to basically do 5.2 times 10 to the 4. If you're putting this in your calculator, make sure you put parentheses in between these. I found that it just makes it just a little bit easier to not make a mistake. And if you want to put it in the calculator all at once at the same time, you can. But to do that, you'll want this extra set of parentheses. Okay, and I'm actually going to make that extra set of parentheses a completely different color because I really want you to notice them. Okay, otherwise the calculator will not realize that you want to multiply these two things and then divide. It won't do it right. Okay, so then once I do that, I get 1.72 times 10 to the 5 cubic feet. Okay, now they mentioned the 65% efficient part, so we need to do that part. We won't be done until we've taken care of this 65% efficient part. So we're going to take this 1.72 times 10 to the 5, and there's two ways you can do it. You can multiply it by 0.65, or you can multiply it by, you can do 1.72. Oh, geez. Okay, 1.72 times 10 to the 5, and you can do this. These are both the exact same thing. So then you'd multiply by 65 and divide by 100. Both of those are the same thing, and they're going to get you the exact same thing. So now let's go ahead and let's get an answer. When you take that, you'll get, when you do that math, you'll get 1.1, you'll get 1 something, so I rounded it to 1.12 times 10 to the 5 cubic feet. And that's how you solve that one. So for this problem, we need to look at, it says how many pounds of water could be raised in temperature 20 degrees Fahrenheit by a 90% efficient burning of 30 cubic feet of natural gas. So that's a lot of stuff we got going on here. So the first thing we want is, let's put this box around the thing that we want. We want how many pounds, and then they're giving us 20 degrees Fahrenheit, 90% efficient, and 30 cubic feet. Okay, so what we're starting with is that 30 cubic feet. So let's go ahead and put that. Okay, and then what we want to do is we want to use that previous slide, that information they gave us in the previous slide that said there's 1,031 BTUs per 1 cubic foot. Okay, and this is going to get us to convert it to feet, and we need BTUs because we need BTUs to get to pounds. So it's a little bit of a process. So we're going to do 3,930 once we multiply these two, and our answer will be in BTUs. Okay. Now for step 2, let's take that 3,930 BTUs, and let's multiply that by 90%, which is our 90% efficient. So I'll put this yellow here so you know that's that step. And that's going to give us 27,837 BTUs. Okay, now we're going to take this and we're going to figure out the answer in pounds. Okay, so let me get another color again. Just kind of help you guys keep track. And this is where we'll use that temperature. Okay, so we're going to take that 27,837 BTUs and we're going to convert it to pounds. Okay, and so 1 BTU is equal to 1, and they call it a pound degree Fahrenheit. Okay, so this is a 1 and then that's a pound. And so we're going to cross out those BTUs, and we want our answer in pounds, so we need to figure out a way to get rid of this Fahrenheit, and luckily they gave us this 20 degrees Fahrenheit. So we can put this 20 degrees Fahrenheit here, and now all we're left with is pounds. So now we can do 27,837 and divide that by 20, and we'll get 1391.85 pounds. Okay, the most common mistake I see with students is they forget to convert it to pounds and they leave their answer in BTU. The other thing that you can do, but it's not required, is you can put the answer in significant figures, but on the AP exam, they let you have the answer however you want. So that's how you do that problem.
We made it through that one. Okay, now part 4 has a couple different ones, and your FRQs are probably not going to be this difficult because you're not allowed a calculator on the exam this year. So basically what we're going to do is the R value is it's 6.7 for a blanket that covers 25 square feet. This is how many BTUs will it save for every hour it prevents 1 degree Fahrenheit of temperature change. So we have a formula on your sheet. I've gone ahead and converted it, rearranged the formula. Okay, and this is basically the formula for R value, and then I'm just, just rearrange the formula. Now, a cool thing on the FRQs is, let's say you got this part wrong, but you got the like part B right, even though part B relies on your answer for part A. If you do the math for part B correctly, you'll still get the points. They still give you the points. So what I like to tell students, if you don't know how to do part A, just make up an answer for part A, and you pick an easy number, and then and then use that answer for part B, and that way it'll, since you're not going to get points for part A anyway, it'll at least save you some effort on part B. Okay, this should actually be 167.5. Okay, and I'm just going to convert this to cubic feet. BTU. So that's one of my BTUs. And this was 1 hour, they said. So if we want to do For a year, we're going to need to do 24 hours, and that's 1 day and 365 days, 1 year. Okay, so that's how much you'll save in a year. Now, let's do 5. 5 is about efficiency. So the first thing we need to do is we need to figure out how many BTUs is this. Okay, so we have 5,000 pounds of water, and then 1 pound is 1 BTU, and then we need to do the 25 degrees Fahrenheit. This is that definition of BTU, remember? Okay. And now we need to figure out what this 210 feet is. Okay. And then whichever one's the largest is going to be on the bottom, because you can't have a machine that is more than 100% efficient. So you can just put the one that is larger on the bottom. Okay. Okay. So this one was the larger one. So now we're going to do 125,000 over 2.7 thousand. And that's going to give us 0.576. And then we just multiply this by 100. That'll give us 57.6%. So this one had 3 steps. Now, number 6. So in this one, we have 7 tons of coal burning, and we're generating 3.6 times 10 to the 4 kilowatts of electricity. So what is the efficiency of the generator? Okay, so this is showing us how many kilowatts. So basically, we're going to take this 7 tons, and we're going to put this in kilowatts. So we have 1 ton is 2.5 times 10 to the 7 BTUs. And then 3413 BTUs is 1 kilowatt hour. Okay, so it's going to give us 5.1 times 10 to the 4 kilowatt hours. And then we can take that And we can put the 3.6 on top of the 5.1. Remember, you're always going to put the bigger number on the bottom because you can't have a machine that's more than 100% efficient. Okay, so this is going to give us 0.705. Multiply that by 100, which is 70.5%. Okay. Now, problem 7 has like a million parts. I don't know if you guys have started on these yet. So let's see what it wants here. It says, if you replace a 75-watt incandescent light bulb with a fluorescent light bulb, it gives you the same amount of light by drawing only 20 watts. And then you use it for 4 hours a day. So basically, we're going to compare the two. Okay, so we've got 75 watts. We need to convert this to kilowatt hours because the answer, it wants our answer in kilowatt hours. So we have 1,000 watts in 1 kilowatt hour. And then, well, kilowatts. We'll get the hour in a second. And then we multiply it by 4 hours. There's our hour. And we end up with 0.3 kilowatt hours. Okay. Now, we can do 20 watts. Same thing. Okay. And now we can just take the difference between the two. So we'll do 0.3 minus 0.08. And we're going to save 0.22 kilowatt hours a day. The next question says, how much would you save in a year? Again, now if you had this answer wrong in part A, or you didn't know how to do part A, you could make up an answer for part A, and then if you did know how to do this one, you could put your answer from part A in here, and you could still get full credit for part B. So that's kind of like a little trick for the FRQs. So we're just going to multiply this by 365. I can write 365. Okay, so I'm going to get 80. Kilowatt hours per year. Okay, let's go to part C. The cost of a kilowatt hour is 10 cents. So how much money does the fluorescent light bulb save in a year? So we're going to take that 80.3 kilowatt hours per year, and we're going to multiply that by 10 cents. And we're going to get, so $8.03 a year, which is, it's nothing to sneeze about. If you have, 50 light bulbs in your house and you convert, that would be 50 times 8, which is, pretty significant savings. Now we have part D. Now for part D, it says it has this little fraction here. I believe they meant a decimal. So just put a decimal there. And so the first thing you need to do is you need to figure out your power. So we have power is equal to current times voltage. So if our current is 0.06 and our voltage is 0.75, our power is going to be 0.045 W. Okay. You may have solved that one before, a similar one like that. Use that formula in physics. Now it says if the solar cell has an area of 20 centimeters squared and collected sunlight when the solar constant was 0.8 watts per centimeter squared, what is the efficiency? Okay, so we need to take that 0.8 watts, 0.08 watts, and multiply that by 20 centimeters squared. Okay. And then now we want the efficiency, so we're going to take that answer we got in like 7D, like that just previous part. So we're going to have 0.0045, and I know that one goes on the top because it's the smaller number, and the smaller number always goes on the top when we're doing efficiency. And so I'm going to get 0.02, and we'll multiply that by 100, and it's going to be 2.8%. And that's a pretty small efficiency, but again, we're talking about capturing, light from the sun, so it's going to be very difficult to be very efficient capturing light from the sun. Okay, so how many solar cells would it take to run a 60-watt bulb? Okay, so our solar cell was 0.045 watts, and a 60-watt light bulb is 60 watts. So we're going to do 60 watts divided by 0.045 watts. It's going to be 1334 solar cells. Okay. Now, part E. Okay. If the efficiency of a coal-burning power plant is 65% and the efficiency of energy retransmission is 95% and the efficiency of the electric stove is 85%, how many BTUs of heat would be produced after 50 tons of coal have been burned? Okay. So basically we're going to have to calculate the efficiency 3 times after we've converted this 0.5 to BTUs. At least I'm going to convert it to BTUs first. You could, I'm just going to erase this in and start over. You could do your efficiency first. Take all those percentages first, but I don't know. I like doing it at the end. I got this conversion again from that very first chart that's at the top of the problems page. So if it was 100% efficient, this is how many BTUs you'd have. Okay, but it's not. Okay. The first thing is the power plant is going to take some of that efficiency, and it's only 65% efficient. So we're going to do, we have to multiply this by 0.65. Okay. Okay. Now, we're going to lose some energy in that transmission from the energy to your house. Okay? And that is 95%. So that's pretty good. Okay, so that's going to give us 7.72 times 10 to the 6. Now, the last place we're going to lose efficiency is the stove. Okay, so the stove is 85% efficient. So let's figure that out. Okay, so this will be our answer. Okay. This I believe. Oh, there's one more step. Okay. I'm gonna leave this one. Well, I guess I could do it. I did all the others, so I might as well do this one for you as well. So the first thing we're gonna need to do is basically turn these gallons into pounds. And that conversion, again, is on your sheet. And if these problems seem hard, don't despair. The problems on your FRQs are usually much easier. So if you guys, you've been doing the math on some FRQs now, you can see that those are a little bit easier. So hopefully these problems don't freak you out. So here we go. 1 foot cubed, 10, 31 BTU, 1 BTU is 1 degrees Fahrenheit, 1 pound, 15 degrees Fahrenheit, 6. So I'm just looking at the conversions I have and figuring out what I need to do to get, where I need to be. And I know that I want cubic feet as my answer, so I need to have that at the top, right? So we have 2.33 times 10 to the 4 feet cubed. Now that would be the answer if it was 100% efficient, but it's not. So, and this number was just 75 minus 60. See. That's how I got that number. So now I need to take this 2.33, I need to multiply it by 0.8, and that's going to give me 1.86 times 10 to the 4 feet cubed. Hopefully these problems were helpful to you. Again, I worked them all out for you, one, because I think they're kind of difficult, and two, because I kind of wanted to throw you a bone if you watched the recording or came to the live session. So hopefully this was helpful, and it will save you some time. I'll still be here for the rest of the hour, but